Hello there, and welcome back to Sleepy Wiki. Tonight, we'll embark on a very quiet journey into the heart of the universe's great unknowns. Imagine the cosmos as an ancient, illuminated manuscript, vast and beautiful, yet with certain pages still veiled in an ethereal mist. We're not here to decipher, but simply to contemplate, as we drift through 10 of the most profound unsolved mysteries in physics. From the invisible embrace of dark matter to the enigmatic whispers of quantum foam, these are the questions that keep the universe beautifully mysterious. We'll explore them not with urgency, but with the gentle curiosity of a starlit night, inviting wonder without the need for immediate answers. If these quiet explorations bring a sense of peace to your evening, a soft like or a gentle subscribe would be deeply appreciated, helping more sleepy wanderers find their way to our quiet corner of the internet. Now, as the world outside grows still, let us quietly begin with the first of our 10 unsolved mysteries in physics. As we drift further into the quiet cosmos, where starlight paints distant galaxies across an infinite canvas, we encounter whispers of something profound, something unseen, yet undeniably present. Our universe, vast and glittering with all the stars and nebula we can perceive, holds a secret far grander and more elusive than its visible splendor suggests. It's a secret woven into the very fabric of existence, a silent conductor orchestrating the cosmic ballet, dark matter. Imagine, for a moment, a grand waltz taking place on a colossal, invisible stage. Billions of stars, each a tiny dancer, twirl gracefully around the luminous hearts of their galaxies. If you were an observer, you'd naturally expect the dancers on the outer edges of this celestial performance to slow down, much like children on a carousel spin, slower the further they are from the center. Gravity, you see, should weaken with distance. The visible matter, the stars, the gas, the dust that glows with familiar light, should be the only source of this gravitational pull, dictating the tempo of the cosmic dance. But when pioneering astronomers, like the remarkable Vera Rubin in the 1970s, meticulously measured the speeds of these distant stars and gas clouds in the spiral arms of galaxies, they found something truly astonishing. The outer dancers were twirling just as fast, sometimes even faster, than those closer to the gravitational center. It was as if an unseen hand was lending them an extra powerful push, preventing them from being flung out into the desolate cold of intergalactic space. The visible matter simply wasn't enough to hold these colossal structures together. Without something else, something invisible but gravitationally mighty, galaxies should have spun themselves apart eons ago. This discrepancy, this silent anomaly, was one of the first profound clues to dark matter's existence. It suggested a vast, enveloping halo of unseen mass, extending far beyond the luminous boundaries of galaxies, providing the extra gravitational glue needed to keep them intact. It's like a colossal, invisible framework, a ghostly scaffolding upon which the visible universe is built. Our journey into the unseen doesn't stop with spinning galaxies. Think of a colossal, invisible magnifying glass, suspended in the cosmic ocean. When light from a far-off galaxy passes through a massive galaxy cluster, it gets bent and distorted, much like peering through the wavy glass of an ancient window. This phenomenon is called gravitational lensing, Einstein's theory of general relativity beautifully predicts this bending of space-time by mass. What's remarkable is that the amount of bending, the sheer warping of space-time we observe in these cosmic lenses, is far greater than what the visible galaxies and hot gas in the cluster could possibly produce. The light is being bent by a mass 5 to 6 times greater than what we can see, indicating that the bulk of these clusters' mass is, once again, dark and unseen. It's as if a phantom presence is flexing its gravitational muscles, shaping the very paths of light itself. And even the echoes of the Big Bang, the faint cosmic microwave background radiation, the very first light emitted in our universe, tells a similar tale. Tiny ripples and patterns in this ancient light reveal the early universe's composition, hinting at a universe where ordinary matter was vastly outnumbered by its dark counterpart. And when scientists run computer simulations of how the grand structures of the cosmos, the vast webs of galaxies and galaxy clusters, formed over billions of years, these simulations only create a universe that looks like ours, if dark matter is the dominant gravitational player, providing the initial seeds and scaffolding for everything to coalesce around. Without it, the universe would be a far emptier, far less structured place. So, what exactly is this invisible architect? What makes it so elusive? The very name dark matter offers a clue. It's dark, not in a scary way, but in the sense that it doesn't interact with light at all. It doesn't glow, it doesn't reflect, it doesn't absorb. It's truly invisible to our telescopes, which are, after all, just sophisticated light collectors. Furthermore, it doesn't seem to interact with the strong nuclear force, which binds atomic nuclei, or the weak nuclear force, which governs radioactive decay, except perhaps incredibly subtly. Its primary interaction with the universe seems to be through gravity. This means it's not made of the familiar stuff that makes up stars, planets, or even you and me. That's called baryonic matter. Instead, scientists theorize that dark matter is composed of entirely new types of particles, particles not found within our current standard model of particle physics. Imagine entirely new species of subatomic particles passing through us and everything around us almost entirely unnoticed. One leading candidate for these mysterious particles is called a WIMP, a weakly interacting massive particle. The name itself describes its key features. Weakly interacting means it rarely bumps into ordinary matter, explaining its elusive nature, and massive means it carries enough mass to exert the powerful gravitational pull we observe. Other candidates include ultralight axions, or even sterile neutrinos, each a theoretical whisper of a new fundamental component of reality. And how much of it is there? When we add up all the evidence, we find that dark matter isn't just a minor constituent. It constitutes about 27% of the total mass and energy of the universe. Compare that to the paltry 5% that makes up all the visible stars, planets, and gas, the ordinary matter we know and love. The rest, an even more enigmatic 68%, is dark energy, a topic for another quiet journey into the unknown. So, what we see, what we perceive with our senses and instruments, is merely a shimmering, iridescent foam atop a vast, unseen ocean of dark matter. So, how do we search for something that leaves no trail of light, something that barely interacts with anything we know? It's like trying to catch a whisper in a hurricane or feeling for a ghost in a crowded room. Scientists around the world are engaged in a patient, ingenious quest. Deep underground, shielded from cosmic rays that could mimic their signals, sensitive detectors lie in wait, hoping to feel the faint, fleeting touch of a dark matter particle passing through. Other experiments in space look for indirect signs like faint gamma-ray emissions that might be produced when two dark matter particles annihilate each other. And powerful particle accelerators, like the Large Hadron Collider, try to smash known particles together with such force that they might produce a dark matter particle even for a fleeting instant. This vast, silent ocean of dark matter, with its unseen influence, is a profound reminder of how much more there is to learn about our cosmic home. It's a testament to the fact that reality is far richer and stranger than our everyday experiences might suggest. And as we ponder this magnificent, invisible architect of the cosmos, remember that every mystery, however profound, is an invitation to wonder, to learn, and to dream. But the universe's secrets don't end with this unseen scaffolding. Beyond the gravitational embrace of dark matter lies an even stranger phenomenon, a force that doesn't pull galaxies together but pushes the very fabric of space apart. Picture yourself drifting through an endless ocean of galaxies, watching them slowly dance through the cosmic dark. For most of the 20th century, astronomers believed this grand waltz was gradually slowing down, like dancers running out of breath. We know from the diligent work of astronomers like Edwin Hubble that this grand tapestry of stars and galaxies is not static. It is expanding. The universe is stretching, growing larger with every passing moment, much like a loaf of raisin bread rising in the oven, where each raisin, a galaxy, moves further away from its neighbors as the dough expands. For a long, long time, scientists believed that while the universe was expanding, its own immense gravity, the collective pull of every star, every galaxy, every particle of matter, should be acting like a gentle cosmic brake. They expected the expansion to be slowing down, gradually over billions of years. It's a bit like throwing a ball into the air. It shoots upwards with initial force, but gravity soon begins to win, slowing the ball's ascent until it eventually pauses and begins to fall back down. The universe, too, with all its matter, should have been slowing its outward journey, losing momentum from that initial colossal push we call the Big Bang. But then, something astonishing happened in the late 1990s. A dedicated group of astronomers, including pioneering scientists like Saul Perlmutter, Adam Rees, and Brian Schmidt, set out to measure this cosmic deceleration. To do this, they relied on very special cosmic beacons, which we call Type Ia supernovae. Imagine these supernovae as exquisite cosmic lighthouses scattered across the vast ocean of space. These aren't just any exploding stars, they are, in a beautiful twist of astrophysics, what we call standard candles. This means that each Type Ia supernova, when it explodes, reaches almost exactly the same peak intrinsic brightness, no matter where it is in the universe. It's like having a specific brand of light bulb that you know always emits the same amount of light. By carefully observing these distant stellar explosions, scientists could measure how bright they appeared from Earth. The dimmer a light appears, the further away it must be. If the universe's expansion was slowing down, these distant supernovae, which we see as they were billions of years ago, should have appeared brighter than they would if the expansion were speeding up, because they would have been closer at that point in time. It was a painstaking and monumental task, peering back across unimaginable stretches of space and time to capture the ancient light from these dying stars. And what they saw was profoundly unexpected. The light from these most distant supernovae was fainter than their models predicted, much fainter. This wasn't a subtle difference. It was a clear signal that these cosmic lighthouses were further away than they should have been if the universe's expansion was slowing down. In fact, the only way for them to be so far away, so much dimmer, was if the expansion of the universe was not slowing down at all. Instead, it was speeding up. The cosmic brake wasn't on. A cosmic accelerator was pressed down. This discovery sent ripples of awe and confusion through the scientific community. It earned Perlmutter, Rice, and Schmidt the Nobel Prize in Physics in 2011, recognizing the sheer audacity and significance of their finding. To explain this cosmic defiance, this acceleration, scientists were compelled to invent something entirely new, something they had never directly observed before. They called it dark energy. Dark energy is not dark matter, which we explored earlier as the invisible gravitational glue holding galaxies together. Dark energy is something else entirely. It's not matter, it's not radiation, it doesn't cluster in galaxies or form stars. Instead, it's envisioned as a mysterious, repulsive force, an inherent property of space itself that acts in direct opposition to gravity. Picture it as an invisible, gentle but utterly relentless hand, subtly pushing the fabric of the universe apart, causing the expansion to accelerate. This enigmatic entity is truly dominant in our universe. Current estimates suggest that dark energy makes up a staggering 68% of the entire energy density of the cosmos. Think about that for a moment. Nearly 3/4 of everything that drives the universe is something we cannot see, cannot touch, and understand only by its effect on the largest scales. Ordinary matter, the stuff of stars, planets, and ourselves, accounts for only about 5%, and dark matter for about 27%. What makes dark energy so powerful in driving this acceleration is a peculiar property. Unlike matter and radiation, whose densities dilute as the universe expands, dark energy's density appears to remain constant. Imagine that expanding loaf of raisin bread again. As the dough expands, the raisins, galaxies, spread out, becoming less dense. If there were a form of energy inherent in the dough itself, and as the dough stretched, more of that energy magically appeared in the newly created space, then that energy would never thin out. That's essentially what we believe dark energy does. As space expands, new space is created, and with it, new dark energy, maintaining its constant density. This continuous infusion of repulsive energy is what keeps the cosmic accelerator pressed, pushing galaxies further and faster apart. So, what exactly is dark energy? This is the core of the mystery. The leading candidate is something Einstein himself briefly considered and then discarded as his biggest blunder: the cosmological constant. This idea suggests that empty space itself possesses a tiny intrinsic energy. A vacuum, it turns out, might not be entirely empty. It could be seething with virtual particles popping in and out of existence, contributing to this inherent energy. The problem is when physicists try to calculate this vacuum energy based on quantum mechanics, their predictions are astronomically larger than what we actually observe, by a factor that makes even the largest numbers seem small. This enormous discrepancy, a difference of 120 orders of magnitude, is one of the biggest theoretical challenges in all of physics. Now, other ideas propose a more dynamic field, perhaps something called quintessence, an evolving energy field that pervades the universe. But these are just whispers in the cosmic dark, elegant mathematical concepts attempting to grasp a reality that remains stubbornly elusive. The implications of dark energy are immense. It's steering the ultimate destiny of our universe. If dark energy continues its relentless push, the universe will expand forever, growing colder, emptier, and darker until all stars burn out and all galaxies are too far apart to even see each other. This chilling fate is often called the Big Freeze, or heat death. If, however, dark energy were to grow stronger over time, it could lead to a catastrophic Big Rip, where the repulsive force eventually tears apart galaxies, stars, planets, and even atoms themselves. For now, the consensus leans towards a future of continued, accelerating expansion leading towards the Big Freeze. But the very nature of dark energy remains the biggest unanswered question in cosmology, a cosmic whisper that demands our attention, even as it slips through our fingers. So, as you drift into slumber, consider the universe not just as a vast collection of stars, but as a dynamic entity, shaped by forces seen and unseen, understood and profoundly mysterious. Dark energy reminds us that the cosmos holds secrets far grander and stranger than we can yet fully comprehend. It's a testament to the power of observation, to the courage of scientists who dare to challenge established beliefs, and to the endless wonder that awaits us when we look beyond the obvious. While dark energy shapes the universe on the grandest scales imaginable, steering the destiny of cosmic superclusters, another mystery awaits us at the opposite extreme. In the realm of the infinitesimally small, where the rules of reality seem to shift entirely. Two magnificent pillars of understanding stand tall in the vast cathedral of physics. Each pillar, forged from brilliant minds and countless experiments, supports an immense dome of knowledge, revealing breathtaking vistas of our universe. One pillar, shimmering with an ethereal glow, unveils the secrets of the infinitesimally small, the very fabric of reality at its most fundamental level. This is the realm of quantum mechanics. The other, grand and stoic, charts the cosmic dance of planets, stars, and galaxies, revealing the majestic curvature of space-time itself. This is the domain of general relativity. Both are extraordinarily successful, predicting phenomena with astonishing accuracy within their own spheres. Quantum mechanics allows us to understand the behavior of light and matter at the atomic and subatomic scales, leading to technologies like lasers, transistors, and medical imaging. It whispers to us of a universe where particles aren't just tiny balls, but elusive waves of probability, where existence itself is a matter of chance and observation. General relativity, on the other hand, describes gravity not as a force pulling objects together, but as a warping of space and time caused by mass and energy. It predicts the existence of black holes, the expansion of the universe, and the subtle bending of starlight around massive objects. It has allowed us to navigate across continents with GPS satellites, each tick of their atomic clocks precisely adjusted for the tiny gravitational differences between Earth and orbit. They are, in essence, two different languages describing two different facets of the same profound reality. Quantum mechanics speaks in riddles of uncertainty, of energy packets called flash quanta, of particles that can be in multiple places at once until observed. Picture it like a deep, dark forest at twilight, filled with the soft rustling of unseen creatures, the whisper of leaves, and the elusive dance of fireflies. Nothing is perfectly still or entirely predictable. Everything shimmers with possibility, a tapestry woven from probabilities. When you try to pinpoint an electron's exact position and its exact speed simultaneously, quantum mechanics gently reminds you that the universe simply doesn't allow such absolute certainty. It's like trying to perfectly still a shimmering piece of silk while also measuring its exact flow in a breeze. The very act of measurement affects what you're trying to know. This world is inherently lumpy, granular, made of discrete packets of energy and matter, like individual grains of sand making up a beach. Now, shift your gaze to the other pillar, general relativity. It speaks in the grand, sweeping prose of continuous curves and smooth geometries. Imagine a vast, perfectly stretched trampoline. When you place a bowling ball on it, the fabric dips, creating a gentle curve. A marble rolling nearby isn't pulled towards the bowling ball. It simply follows the curve in the fabric. That, in essence, is how general relativity describes gravity. Massive objects warp the fabric of space-time around them, and other objects simply follow the contours of that warp. There are no sudden jerks, no quantum leaps, just the smooth, elegant flow of existence. It's like a calm, boundless ocean where the currents are grand and predictable, the waves rising and falling in continuous undulations. Time itself is not an absolute ticker, but flows differently depending on how close you are to a massive object, slowing down in stronger gravitational fields. Herein lies the profound mystery, the great puzzle that keeps theoretical physicists awake at night. How can these two profoundly successful but seemingly contradictory descriptions of reality both be true? How can the universe be both a granular, probabilistic, shimmering quantum dance and a smooth, continuous, grand relativistic flow all at once? The problem becomes acute, almost painfully so, when we try to apply both theories simultaneously to extreme scenarios. Think of a black hole. At its heart, a singularity, a point of infinite density where all the mass is concentrated. Here, gravity becomes unimaginably strong, and space and time are distorted to an extreme degree, a realm general relativity describes with terrifying elegance. But at such an incredibly small point, the quantum nature of reality, the shimmering probabilities, and discrete quanta must also become vitally important. It's like trying to use a magnifying glass to examine the weave of a tapestry, general relativity's domain of large-scale curves, while simultaneously trying to understand the individual atomic vibrations of the threads themselves, quantum mechanics' domain of tiny particles. The rules that govern the very small seem to break down when confronted with the immense gravitational forces of the very dense. Nor consider the very beginning of our universe, the Big Bang. In those first fleeting moments, all the matter and energy of the cosmos were compressed into an incredibly tiny, incredibly dense point, a singularity even more extreme than a black hole's. To understand what truly happened then, to unravel the ultimate origin story, we need a theory that can seamlessly merge the quantum fuzziness of the very small with the intense gravitational warping of the very dense. When physicists attempt to apply the rules of quantum mechanics to gravity itself, trying to quantize gravity as they have quantized other forces, the equations break down, yielding nonsense like infinite probabilities, a clear sign that our current understanding is incomplete. It's like trying to play a piano and a drum set at the same time, but they're tuned to completely different scales and rhythms. The search for a theory of quantum gravity is therefore the quest for a single, unified framework that can describe reality at all scales, from the smallest subatomic tremor to the grandest cosmic ballet. It's the search for a master key that can unlock the deepest secrets of the universe, allowing us to peer into the heart of black holes and witness the birth of everything. This isn't just about intellectual curiosity. It's about understanding the very texture of space-time itself. Imagine zooming in closer and closer on the fabric of space-time, much like peering through a microscope at a piece of cloth. At our everyday scales, it seems smooth and continuous, just as general relativity describes. But as we zoom in further, beyond the scale of atoms, past even the protons and neutrons, down to incredibly tiny distances known as the Planck length, an unimaginably small 10⁻⁵ meters. What would we see? Quantum mechanics suggests that at this extreme scale, space-time itself would no longer appear smooth. Instead, it would become a chaotic, bubbling, frothing sea of quantum fluctuations, a petals quantum foam. Picture the calm ocean suddenly transforming into a tempestuous, swirling froth, where tiny bubbles of space and time are constantly popping into and out of existence. Here, the very concepts of plage before plage and plage after plage, of plage here plage and plage there plage, might lose their familiar meaning. This is where our two great theories collide and cancel each other out, like two powerful waves meeting head-on, creating a chaotic splash. The leading contenders in this monumental quest, like brave explorers charting unknown territories, include ideas such as string theory and loop quantum gravity. String theory proposes that the fundamental particles of our universe aren't tiny points, but rather unimaginably small, vibrating strings of energy, like the notes on a cosmic violin. The different vibrations of these strings give rise to the different particles we observe, and crucially, one of these vibrational patterns could correspond to the graviton, the hypothetical quantum particle of gravity. If the universe is indeed woven from these vibrating strings, then the conflict between the smooth and the lumpy might simply dissolve. Loop quantum gravity, on the other hand, takes a different approach, suggesting that space-time itself is not continuous but is made up of discrete, interconnected loops, a granular structure much like a chain-mail fabric. These loops weave together to form the fabric of space-time, quantizing space and time themselves. In this view, there's a smallest possible grain of space and time, preventing the infinite densities that plague other theories. Though these theories are complex and still very much under development, without experimental evidence to definitively confirm one over the other, they represent humanity's most ambitious attempts to reconcile these two magnificent descriptions of our universe. The journey is long, the path uncertain, but the prize is the ultimate understanding of reality itself, a unified vision that embraces both the grand symphony of the cosmos and the delicate whispers of the quantum realm. This quest to unite the very large and the very small remains one of physics' greatest challenges. But as we step back from these theoretical heights, let us turn to a mystery rooted in the universe's very first moments, a cosmic imbalance that explains why anything exists at all. And so, as we drift deeper into the quietude of our thoughts, let us turn our gaze not outwards to distant galaxies, but inwards to the very fabric of our being, to a profound cosmic riddle whispered from the dawn of time itself. Imagine, if you will, the universe's very first breath, a moment of unimaginable energy and density we call the Big Bang. It was a time of perfect symmetry, a fleeting instant when the cosmos was an exquisite ballet of creation. In this nascent inferno, theory tells us that matter and antimatter were born in precisely equal measure, like cosmic twins emerging into existence, each a mirror image of the other. For every electron, there was a positron, its antimatter counterpart, identical in mass, but carrying an opposite electric charge. For every proton, an antiproton, similar in all but its charge. They were, in essence, perfect reflections, destined to dance together in the cradle of the cosmos. Now, here's where the story takes a curious turn, a twist in the grand cosmic narrative. These cosmic twins, matter and antimatter, share a peculiar, almost poetic destiny. When they encounter each other, they don't just combine, they annihilate. It's not a violent explosion in the chaotic sense, but rather a brilliant, silent disappearance, a transformation into pure energy, typically in the form of photons, packets of light. Picture two intricately designed snowflakes, each a perfect inverse of the other, touching for the first time. And instead of merging, they simply vanish in a soft, ethereal glow, leaving only warmth and light behind. This process is incredibly efficient. Mass is converted into energy with absolute precision, following Einstein's famous equation, E=mc2. In the early universe, this annihilation would have been happening constantly, a cosmic fireworks display of creation and disappearance. Given this beautiful yet destructive symmetry, you would expect our universe today to be either completely empty, having annihilated itself into a sea of photons, or to contain vast regions of matter existing alongside equally vast regions of antimatter. It would be a cosmos divided, a grand chessboard where dark and light pieces coexisted in balance. But that, my dear listeners, is not the universe we inhabit. Look around you, at your hand, at the gentle glow of the stars outside your window, at the very air you breathe. It's all matter, from the smallest atom in your body to the largest supercluster of galaxies. The cosmos, as far as our most sophisticated instruments can peer, is overwhelmingly composed of matter. We haven't found any significant pockets of antimatter galaxies or antimatter stars. If there were entire anti-worlds out there, their boundaries with matter worlds would produce gamma-ray signals that would be unmistakable, yet silence. This presents us with one of physics' most profound and enduring mysteries. Where did all the antimatter go? If the Big Bang created them equally, how did matter emerge victorious, leaving behind barely a trace of its twin? It's as if, after a magnificent cosmic party, one of the identical hosts simply vanished into thin air, leaving only their sibling to greet the dawn. Physicists ponder this cosmic imbalance with a sense of awe and determination. The standard model of particle physics, our most successful theory describing the fundamental particles and forces, largely predicts a universe of perfect symmetry. Yet, the universe we observe is anything but. It hints at a subtle, perhaps even infinitesimal, deviation from that perfect balance, a cosmic oops that allowed matter to gain a slight edge in the very first moments after the Big Bang. The leading hypothesis, a concept as delicate as a butterfly's wing, suggests that there was a tiny microscopic asymmetry in the way matter and antimatter behaved during those initial turbulent seconds. This is often referred to as CP violation, a technical term that essentially means that some fundamental particles and antiparticles didn't decay or interact in exactly the same mirrored way. Imagine two dancers supposedly performing perfectly synchronized steps. What if just occasionally one dancer took a slightly different stride or twirled just a fraction of a second slower? This minuscule difference, repeated billions upon billions of times, could have led to a grand imbalance. Think of it this way. For every billion pairs of matter and antimatter particles that annihilated into pure energy, perhaps there was just one extra matter particle left over. Just one out of a billion. It seems impossibly small, doesn't it? Like finding a single grain of sand on a vast beach that's slightly different from all the others. But in the colossal scale of the early universe, where particles were created and destroyed in unfathomable numbers, that tiny, persistent preference for matter was enough. It was the crucial sliver of difference that allowed our universe, with its stars, planets, and even you, to exist. Without that imbalance, there would be no matter left to form anything at all, only an endless sea of light, a universe of pure energy, devoid of structure or life. This process, where the initial matter-antimatter symmetry was broken to produce the observed excess of matter, is known as baryogenesis. It required very specific conditions in the early universe, conditions that allowed this subtle favoritism to play out. These include a universe that was out of thermal equilibrium, meaning it wasn't perfectly smooth and uniform in temperature, and the aforementioned violations of fundamental symmetries like CP symmetry. Researchers are meticulously studying particle interactions in powerful accelerators here on Earth, seeking even the slightest deviations in how matter and antimatter particles decay. These subtle differences, observed in experiments involving particles like kaons and bosons, offer tantalizing clues like faint footprints in cosmic dust, pointing towards the mechanism that tipped the scales. We also send sophisticated instruments, like the Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station to gaze into the cosmic abyss, searching for any lingering traces of primordial antimatter that might have survived or been created in exotic events. We look for anti-helium nuclei, which would be a sure sign of distant antimatter regions, but so far, the cosmos remains stubbornly matter-dominated. The universe, it seems, made a choice, or rather, a slight deviation from perfect symmetry that allowed existence as we know it to blossom. This missing antimatter isn't just a puzzle for physicists. It's the fundamental reason we are here. It's the silent, profound answer to the question of why there is something rather than nothing. And as we continue our gentle exploration of these cosmic enigmas, remember that every unsolved mystery is not a gap in our knowledge, but an open door, inviting us to look deeper, to wonder more profoundly, and to marvel at the universe's endless capacity for surprise. As the night deepens, let us softly shift our focus from this cosmic imbalance, this tale of missing twins, to another profound secret the universe holds close: the elusive nature of dark matter and dark energy, the invisible forces that shape the very destiny of the cosmos. Join me, won't you, as we next explore the unseen architects of our universe, lingering just beyond the veil of our perception. The deepest, most profound silence in the universe isn't the absence of sound, but the presence of something so powerful that it bends the very rules of reality around it. Black holes, these ultimate gravitational titans, twist the fabric of space-time in ways that challenge everything we thought we knew. Now, our understanding of gravity, thanks to the brilliant mind of Albert Einstein and his theory of general relativity, tells us that it's not some invisible force pulling things, but rather the very shape of the universe being warped by mass and energy. Think of space-time not as an empty void, but as a vast, invisible fabric, like a tightly stretched trampoline. Planets, stars, and galaxies are like marbles or bowling balls placed on this fabric. They create dimples, curves, and dips. And when other objects roll nearby, they aren't pulled by a force. They simply follow the curves in the fabric. It's an elegant dance of geometry and cosmic ballet. Now, imagine an object so incredibly massive, so extraordinarily heavy, that it creates not just a dimple, but a bottomless well in this cosmic fabric. This is the birth of a black hole. It typically begins when a giant star, far heavier than our sun, perhaps 20 times its mass or more, reaches the end of its life. It runs out of fuel for its internal nuclear furnace. The outward pressure that battled gravity for billions of years suddenly wanes, and with nothing left to hold it up, the star collapses in on itself under its own immense weight. It shrinks and shrinks and shrinks beyond anything we can truly comprehend, packing an unimaginable amount of mass into an incredibly tiny volume. As this titanic star implodes, its gravity grows ever more intense, concentrating into an incredibly small space. There comes a point, a boundary, where the escape velocity, the speed you'd need to travel to break free of its gravitational pull, exceeds the speed of light itself. This boundary is called the Hall event horizon. It's not a physical surface you could stand on, but rather a cosmic one-way door. Think of it like a waterfall in the river of space-time. Once you tumble over the edge, no matter how fast you swim, the current is simply too strong and you're inexorably carried downstream. From beyond the event horizon, nothing, not even light, can escape. That's why they appear black to us. They are not actually empty spaces, but regions where gravity has become so dominant that light itself is trapped within their grasp. And because light carries information, once something crosses that event horizon, it's effectively cut off from our observable universe, its secrets locked away forever, leaving us only with tantalizing questions. And where does everything that crosses the event horizon go? According to our current understanding, all that matter and energy continues to collapse inward, past the event horizon, crushing into an infinitely small, infinitely dense point at the very heart of the black hole. We call this a singularity. Here, all our known laws of physics, all our beautiful equations that describe the universe simply break down. Space and time as we understand them cease to have meaning. It's a point of ultimate extremity, a cosmic knot where reality ties itself into an impossible configuration, a place where our current scientific language falls silent. And if you were to fall into a black hole, and please let's just imagine it from a safe distance, comfortably tucked in your bed, you wouldn't just feel a gentle pull. The gravitational force near a black hole is not uniform. The part of your body closer to the singularity would feel a much, much stronger pull than the part further away. This difference in gravitational pull is called tidal force. And it would be so immense, so overwhelmingly powerful, that you would be stretched and elongated like a piece of cosmic spaghetti until your body was torn apart atom by atom. This rather dramatic-sounding process is known as spaghettification, a stark reminder of the extreme power of these cosmic leviathans. For a long time, it was thought that nothing could ever escape a black hole. They were perfect cosmic prisons. But then, a brilliant physicist named Stephen Hawking proposed something revolutionary. He suggested that black holes aren't entirely black. Due to strange quantum effects happening right at the edge of the event horizon, black holes can actually emit a faint glow of particles, slowly radiating away their mass over incredibly long timescales. We call this Hawking radiation. It's like a cosmic whisper, a tiny leak from the universe's ultimate drain, a ghostly emanation that suggests even the most formidable prison walls can eventually erode. This idea, while elegant, created one of the biggest unsolved mysteries in physics, the information paradox. If a black hole eventually evaporates through Hawking radiation, what happens to all the information about the matter that fell into it? Does it truly disappear, violating a fundamental principle that information can never be truly destroyed? Or is it somehow encoded in the Hawking radiation, subtly escaping back into the universe, like a coded message carried on the cosmic winds? We don't yet have the full answer, and it's a profound puzzle that hints at a deeper yet undiscovered connection between gravity and quantum mechanics. Black holes come in different sizes, from high stellar mass black holes, which are typically 3 to 100 times the mass of our Sun, born from collapsing giant stars, to high supermassive black holes, which are millions or even billions of times the mass of our Sun. Almost every large galaxy, including our own Milky Way, harbors a supermassive black hole at its very center, acting like a cosmic anchor around which the entire galaxy slowly spins. They play a vital, if still mysterious, role in the formation and evolution of galaxies, actively shaping the cosmic landscape through their immense gravitational influence. So, even with all we've learned, black holes remain profound enigmas. What truly happens at the singularity? Can we unify Einstein's majestic theory of general relativity, which describes gravity and the large-scale universe, with quantum mechanics, which describes the tiny subatomic world? The extreme conditions inside and around black holes are the ultimate testing ground for such theories, pushing the boundaries of our understanding to their absolute limits. 1. They are not just distant cosmic objects. They are cosmic laboratories, whispering profound questions about the nature of space, time, gravity, and the very fabric of reality itself. They remind us that the universe holds wonders and mysteries far beyond our current grasp, inviting us to keep exploring, to keep dreaming, to keep asking, why? As we drift away from these silent, powerful giants that warp space-time, let's carry with us this sense of wonder, this gentle reminder that the universe is full of secrets yet to be uncovered. Perhaps, as you close your eyes tonight, you might imagine the subtle hum of Hawking radiation, or the gentle curve of space-time beneath your own resting planet. Tomorrow, or perhaps another night, we'll continue our journey into the unknown, exploring another grand puzzle that keeps physicists gazing at the stars. Perhaps the mystery of dark matter and dark energy, the unseen scaffolding of the cosmos. In the heart of quantum reality, a world far smaller than anything our eyes can perceive, we encounter one of physics' most profound and beautiful enigmas, the quantum measurement paradox. Here, we encounter one of physics' most profound and beautiful enigmas, the quantum measurement paradox. Imagine for a moment a single tiny light switch, no bigger than a speck of dust. In our everyday world, that switch is either on or off, simple, definite. But in the quantum realm, things are far more whimsical. Our tiny quantum switch could exist in a wondrous state we call superposition. It's not on and it's not off. It's somehow both, on and off at the very same time. Like a coin spinning in the air, for that fleeting moment, it's neither heads nor tails. It holds the potential for both, simultaneously awaiting its destiny to land. This isn't just a clever turn of phrase. It's the bedrock of quantum mechanics. Particles, like electrons or photons, don't just exist in one place or have one property. Instead, they exist as a cloud of probabilities, a blur of all possible states at once. They are like musical notes that contain all possible melodies until one is played. This inherent fuzziness, this potentiality, is their fundamental nature until something happens. And what is that something? Well, that's where our paradox begins. It's the moment we try to measure or observe our tiny quantum switch. The instant we interact with it, perhaps by shining a light on it or trying to detect its state, that magical superposition vanishes. The spinning coin lands, and suddenly, definitively, it's either heads or tails. The cloud of possibilities collapses, and our switch is now either clearly on or clearly off. But here's the profound mystery. What precisely causes this collapse? And how does it choose which definite state to settle into from all those possibilities? To truly grasp the strangeness, let's revisit a famous experiment, often called the double-slit experiment. Picture a stream of tiny, tiny particles, let's say electrons, being fired at a screen with two narrow slits in it. On the other side of the slits, there's another screen that records where the electrons land. If electrons were like tiny little bullets, we'd expect them to go through one slit or the other, creating two distinct bands on the detector screen, right? Just like if you shot marbles at a wall with two gaps. But that's not what happens. When left to their own devices, unobserved, these electrons behave like waves. They don't just go through one slit, they seem to pass through both slits at once, creating an interference pattern on the detector screen, a series of bright and dark bands, just like ripples in water when two waves meet. It's as if each electron, in its quantum superposition, is exploring both paths simultaneously before arriving at the screen. Now here's the truly mind-bending part. If we place a detector at the slits to see which slit each electron goes through to observe its path, something astonishing happens. The interference pattern disappears. Instead, we get those two distinct bands, as if the electrons suddenly decided to behave like ordinary bullets, choosing just one slit. It's almost as if the very act of watching them forces them to pick a single path, stripping away their wave-like both paths at once nature. The electron's superposition collapses into a definite state simply because we tried to find out what it was doing. This is the heart of the measurement paradox. It's not just a technical detail, it's a fundamental challenge to our understanding of reality. Does reality only become concrete when we observe it? Are objects truly real with definite properties, or are they a haze of potential until a measurement brings them into focus? It's a bit like asking if the moon is there when no one is looking at it, but on a much deeper, more fundamental level. This paradox was famously highlighted by Erwin Schrödinger with his chilling yet illuminating thought experiment. Schrödinger's cat. Imagine a hypothetical sealed box containing a cat, a vial of poison, and a quantum device that has a 50-50 chance of triggering the vial's release based on the state of a quantum particle, say, whether it's spin up or spin down. According to quantum mechanics, until someone opens the box and observes the particle, that particle is in a superposition of both states. And because the cat's fate is linked to the particle, the cat itself would, astonishingly, be in a superposition of being both dead and alive at the same time. Only when the box is opened does the superposition collapse, and the cat is definitively found to be either alive or dead. Of course, we never actually put cats in such boxes, nor do we believe cats are genuinely dead and alive simultaneously. The thought experiment beautifully illustrates the absurdity that arises if we try to apply quantum rules, which work so perfectly for tiny particles, to our macroscopic everyday world. It pushes us to confront the question, where exactly does the quantum world end and the classical world, with its definite on or off states, begin? What counts as a measurement? Is it a conscious observer? Is it any interaction with a complex system? Is it the irreversible recording of information? scientists have grappled with this profound question for nearly a century, proposing various interpretations to make sense of the paradox. The most widely held view for a long time was the Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg. It essentially says that quantum states are inherently probabilistic, and the act of measurement causes the wave function, which describes the particle's probabilities, to collapse into a single definite outcome. It doesn't explain how or why the collapse happens, simply stating that it does. It's a bit like saying, when the coin lands, it's either heads or tails, without explaining the physics of the coin landing, just accepting the outcome as fundamental. Then, there are more radical ideas, like the captivating many worlds interpretation proposed by Hugh Everett III. This interpretation suggests there is no collapse at all. Instead, every time a quantum measurement is made, the universe splits into multiple parallel universes, one for each possible outcome. In one universe, our quantum switch turns on. In another, it turns off. In one universe, Schrödinger's cat is alive. In another, it is dead. All possibilities are realized, each in its own separate reality, constantly branching off into an infinite cosmic tree. It's a breathtaking vision, suggesting an unimaginably vast tapestry of realities constantly unfolding around us, even as we perceive just one. Other interpretations include hidden variables theories, suggesting there's a deeper, as yet unknown reality guiding the particles, or objective collapse theories, which propose that collapse happens spontaneously when a quantum system reaches a certain size or complexity without the need for an observer. Each offers a different story, a different way to paint the picture of reality at its most fundamental. But the fact remains, we don't truly know which, if any, of these interpretations is correct. The quantum measurement paradox stands as a luminous beacon of the unknown, reminding us that even with all our scientific progress, the very nature of what is real and how it comes into being remains one of the universe's most cherished and profound secrets. It invites us to ponder the depths of existence and our place within it, gently challenging our intuitive grasp of reality. And perhaps it's a beautiful thought to hold as we rest, that reality itself is more fluid, more mysterious, and more wondrous than we often imagine. As the quantum realm whispers its secrets, let's consider another profound enigma, one that stretches not into the microscopic, but into the vast, echoing darkness between the stars. The mystery of dark matter and dark energy, a cosmic riddle that hints at an unseen universe lurking just beyond our reach. We find ourselves now at the edge of an even grander mystery, one that stretches back to the very first moments of existence. The universe, not as it is now, vast and intricate, but as an unimaginably tiny speck, hot and dense beyond all comprehension. This was the universe, just fractions of a second after its fiery birth, an infant realm brimming with potential. Yet, as scientists peered closer at the remnants of that infant universe, particularly the faint glow of the cosmic microwave background, the oldest light we can ever hope to see, they found something peculiar. This ancient light, bathing us from every direction, is almost perfectly uniform. It's like finding a tapestry woven across an entire cosmos, where every thread, no matter how far apart, is the exact same color and texture. How could regions of the universe, so distant from one another that light couldn't possibly have traveled between them to even out their temperatures or properties end up so strikingly similar. This puzzle is known as the horizon problem, and it's akin to discovering two distant islands, never having shared a single message, yet having identical flora and fauna. Then there was another puzzle, equally profound, the flatness problem. Our universe, it turns out, is remarkably flat in its geometry. Think of it like the surface of a vast, tranquil ocean, appearing perfectly level for as far as the eye can see. If our universe were curved, like the surface of a sphere or a saddle, it would have either collapsed back on itself or expanded so rapidly that it would be almost empty. Yet, it sits precisely on the knife edge of flatness, a perfect balance that seems almost miraculous. It's as if a cosmic architect meticulously ensured its geometric perfection. For this to happen naturally, the early universe would have had to be impossibly flat from the start, fine-tuned to an exquisite degree. These perplexing observations led brilliant minds to propose a radical yet elegant solution: cosmic inflation. Imagine, not a gentle unfurling, but a sudden, violent growth spurt of the universe. This wasn't just any expansion. It was an expansion so rapid, so exponential, that it's almost beyond our everyday intuition. In an incredibly brief flash, lasting perhaps less than a trillionth of a trillionth of a trillionth of a second, that's 10 to 36 to 10 to 32 seconds, the universe is thought to have swelled by a factor of at least 10 to 26, possibly far, far more. To grasp this, picture a speck smaller than a single atom suddenly inflating to the size of a grapefruit in an instant. Then, continue that expansion, and that grapefruit-sized region becomes larger than our entire observable universe. This incredible burst of expansion provides answers to our cosmic puzzles. For the horizon problem, inflation suggests that all the vast, smooth regions we observe today actually originated from a single, tiny patch of the early universe, a patch small enough for light and information to travel across, allowing it to reach a uniform temperature and density. Then, inflation stretched this uniform patch to unimaginable scales, blowing it up like a balloon being expanded to the size of the Earth. What were once neighbors in a tiny, causally connected garden became distant galaxies in an expansive cosmos, retaining their initial uniformity because they all came from that same well-mixed origin. The flatness problem, too, finds its resolution in this cosmic growth spurt. Imagine inflating a wrinkled balloon to an enormous size. As it expands, any creases or curves on its surface become flatter and flatter, eventually appearing smooth and flat from the perspective of an ant crawling upon it. Inflation similarly smoothed out any initial curvature the universe might have had, driving its geometry towards the perfect flatness we observe today. It essentially ironed out the universe, making it geometrically pristine. And what powered this astonishing expansion? Scientists hypothesize it was driven by a mysterious entity called the inflaton field. Picture this field as a cosmic spring, wound tightly with immense potential energy in the very early universe. This potential energy created a repulsive gravitational force, pushing everything apart with incredible speed. As the inflaton field rolled down its potential energy curve, like a ball rolling down a gentle hill, it released its stored energy, This release of energy didn't just stop the inflation, it also reheated the universe, creating the primordial soup of particles from which all matter and energy we see today would eventually condense. It was a cosmic genesis, turning stored potential into vibrant reality. The idea of inflation isn't just a beautiful story. It makes specific predictions that we can test. The tiny quantum fluctuations that existed in that initial microscopic patch of the universe, when stretched across cosmic scales by inflation, became the seeds for all the structures we see today: galaxies, clusters, and superclusters. These tiny ripples in the fabric of space-time left their imprint on the cosmic microwave background, appearing as slight temperature variations, a cosmic fingerprint of inflation at work. And indeed, observations from satellites like WMAP and Planck have mapped these fluctuations with incredible precision, showing a pattern remarkably consistent with inflationary predictions. But the grand prize, the ultimate smoking gun for inflation, would be the detection of primordial gravitational waves. These are ripples in space-time generated directly by the violent expansion of inflation itself. If detected, they would leave a very specific swirling pattern in the polarization of the cosmic microwave background, known as B modes. It would be like seeing the faint afterglow of the universe's ultimate seismic event, a whisper from creation's earliest moments. The search for these elusive B modes is one of the most exciting endeavors in cosmology today, a testament to humanity's relentless quest to understand our origins. Yet, despite its elegant solutions and observational successes, cosmic inflation remains an enigma in many ways. What is the inflaton field? We don't know. Is it a fundamental field, or does it emerge from something even deeper? What precisely triggered it, and what determined its exact duration and intensity? The details of inflation's beginning and end are still shrouded in mystery. Some theories even suggest that inflation might not have been a one-time event, but an eternal process, continuously spawning new pocket universes within a vast, ever-expanding multiverse. If true, our universe would be just one bubble in an infinite cosmic foam, a breathtaking and mind-bending implication. So, as we contemplate this extraordinary phase of cosmic adolescence, we're left with a theory that brilliantly solves some of the most profound puzzles about our universe's structure, yet simultaneously opens doors to even deeper, more speculative questions. It's a reminder that every answer in science often brings a host of new, fascinating mysteries to ponder. And with that thought gently settling in our minds, let's turn our attention to another profound mystery, one that challenges our understanding of the very fabric of existence itself. The universe is not just filled with stars and galaxies, with light and familiar matter, but also with an ethereal, silent ocean, a sea of countless tiny, nearly massless specters that pass through everything, utterly unimpeded. These are the neutrinos. Picture a ghost, not a scary one, but a gentle, translucent entity that drifts through walls, through mountains, through the very core of our planet, without ever casting a shadow, without ever leaving a trace. That, my dear listener, is a neutrino, and there are trillions upon trillions of them streaming through you, through me, through every inch of space, right this very second, without us ever feeling a thing. Their story began nearly a century ago, not with a direct observation, but with a puzzle, a cosmic riddle that baffled the brightest minds. Scientists were studying a type of radioactive decay called beta decay, where an atomic nucleus transforms, emitting an electron. But here's the curious part. When they meticulously measured the energy of the particles involved before and after the decay, it seemed like some energy had simply vanished into thin air. It was as if you put a puzzle together, and one piece, a vital piece, was simply gone. This was a profound problem, because one of the most fundamental laws of physics states that energy cannot be created or destroyed. It can only change form. It must always be conserved. Enter Wolfgang Pauli, a brilliant and somewhat eccentric physicist who, in 1930, came up with a rather desperate yet ingenious solution. He hypothesized the existence of a tiny, neutral, incredibly light particle that was carrying away the missing energy, a particle so shy, so aloof, that it had managed to escape all detection. He called it a neutrino, meaning little neutral one in Italian, a name later coined by Enrico Fermi. It was a bold idea, a particle nobody had seen, but one that perfectly explained the mystery. It was like postulating the existence of an invisible accountant who quietly balanced the books, even when no one was looking. For years, the neutrino remained a phantom, a mathematical necessity more than a tangible reality. How could one ever hope to detect something that interacts so rarely with matter? Think of trying to catch a whisper in the heart of a roaring waterfall. Neutrinos have no electric charge, so they're not affected by electromagnetic forces. They're immune to the strong nuclear force, the glue that holds atomic nuclei together. Their only interaction is via the weak nuclear force, which, as its name suggests, is incredibly feeble. To give you a sense of just how ghostly they are, a neutrino could travel through a block of lead a light year thick, that's about 9.5 trillion kilometers, without interacting even once. Imagine that journey, unimpeded through a solid wall of matter denser than anything we know. Yet, the universe is absolutely brimming with them. Our sun, that benevolent star that warms our days and lights our nights, is a colossal neutrino factory. At its fiery core, hydrogen atoms are constantly fusing into helium, releasing an astounding torrent of energy and a phenomenal number of neutrinos. Every single second, billions of neutrinos born in the heart of our sun pass through every square centimeter of your body. They sail right through the Earth as if it were empty space, reaching detectors on the other side almost instantly. They are also born in other cosmic cataclysms, like exploding stars, supernovae, carrying away the bulk of the star's energy in a silent, luminous burst of these invisible messengers. But here's where the plot thickened, and the universe presented us with another fascinating riddle. For decades, scientists built increasingly sophisticated detectors, often enormous tanks of special liquid deep underground, shielded from all other cosmic radiation, patiently waiting for that 1 in a trillion chance that a neutrino would gently nudge an atom and reveal its presence. And they did detect solar neutrinos. But there was a problem, a nagging cosmic discrepancy. They were only finding about 1/3 of the number of neutrinos that theoretical models predicted should be streaming from the sun. It was as if the sun was singing, but we were only hearing a fraction of its song. This became known as the solar neutrino problem. For years, this mystery persisted. Was our understanding of the sun's fusion processes wrong? Or was there something fundamentally strange about the neutrinos themselves? The answer, discovered in the late 1990s and early 2000s, turned out to be far more profound than anyone initially imagined, leading to one of the most significant breakthroughs in particle physics in decades. It turns out that neutrinos are cosmic shapeshifters. As they journey from the sun to Earth, they undergo a miraculous transformation, a delicate cosmic dance. You see, neutrinos come in three flavors or types: electron neutrinos, muon neutrinos, and tau neutrinos. The sun primarily produces electron neutrinos. What scientists discovered was that as these electron neutrinos traveled across the vast expanse of space, they would spontaneously change into one of the other two flavors, muon or tau neutrinos, and then back again. This phenomenon is called neutrino oscillation. Imagine three identical yet distinct dancers constantly switching costumes mid-performance, so rapidly that by the time they reach their audience, only a third are wearing the costume you expected. The detectors on Earth were primarily designed to see electron neutrinos, and since many had changed their attire, they simply weren't counted. The sun's song wasn't missing notes. We just weren't listening to all the different instruments. But here's the truly groundbreaking implication of this discovery. For particles to oscillate, to change their identity like this, they must possess mass. Even if it's an infinitesimally tiny amount, it's not zero. This was a monumental revelation because, according to the reigning standard model of particle physics at the time, neutrinos were thought to be massless. The discovery that they do have mass meant there was new physics beyond our current understanding, a deeper layer to reality waiting to be unveiled. It was like finding a secret compartment in a treasure chest you thought was fully explored. Yet, even with this profound insight, the neutrinos continue to guard many of their deepest secrets. We know they have mass, but we don't know their exact mass, nor the precise hierarchy of the three different flavors. Which one is the heaviest, and which the lightest? This is like knowing you have three nested dolls, but not knowing which one is the largest, nor the exact weight of each. And a more fundamental question still remains. Are neutrinos their own antiparticles? Most particles have a distinct antiparticle, like the electron, and its anti-electron, the positron. But for neutrinos, it's possible they are their own ghostly mirror image, a type of particle known as a Majorana fermion. If this is true, it could help explain why our universe is filled with matter, and not an equal amount of antimatter, a cosmic imbalance that allows us to exist at all. These tiny ethereal particles, ever present yet ever hidden, continue to be one of physics' most enduring and fascinating mysteries. Their secrets, whispered across vast cosmic distances, might hold the keys to understanding not just the fundamental nature of matter, but also the very origins and evolution of the universe itself. And as these ghostly particles continue their silent journeys through the cosmos, we turn our gaze to yet another enigma, another layer of reality that challenges our perceptions. We turn our gaze now toward a concept that feels as intrinsic to our existence as breath itself. yet remains one of the universe's most profound enigmas: time. We live within its relentless flow, measuring our lives in moments, days, and years. We watch the clock hands turn, the seasons change, and our own reflections evolve. Time, to us, seems universal, an unwavering rhythm that beats uniformly across the cosmos. But what if time, this seemingly rock-solid foundation of our reality, is far more mysterious, more malleable, and perhaps even less fundamental than we could ever imagine? For centuries, time was perceived as an absolute, an unseen river flowing at a constant speed, carrying all things forward. This was the clockwork universe envisioned by Isaac Newton, where time was merely a backdrop against which events unfolded, unchanging and independent of anything within it. We all shared the same universal now. Yet, as the quiet hum of the universe began to whisper its deeper truths, a brilliant mind named Albert Einstein unveiled a revolutionary perspective, forever altering our understanding. Einstein's theories of relativity revealed that time is not an absolute, but a flexible, intertwined dimension of the cosmos, part of a four-dimensional fabric called space-time. Imagine this fabric not as a rigid grid, but as a vast, ethereal trampoline. When something heavy, like a star or a planet, rests upon it, the trampoline dips and curves. This curvature, Einstein showed, is what we perceive as gravity. But here's the astonishing part. Not only does this cosmic trampoline warp space, it also warps time. This phenomenon is known as time dilation. It means that time doesn't tick at the same rate for everyone, everywhere. Its passage is relative. For instance, if you were to journey near a massive object, like a black hole, where space-time is severely warped, your clock, and indeed your very aging process, would slow down dramatically compared to someone far away. If you spent an hour near a black hole, days, weeks, or even years might pass for your friends back on Earth. It's not just a trick of perception. It's a physical reality. Astronauts on the International Space Station, moving at incredible speeds relative to Earth, actually age slightly slower than people on the ground, though the difference is minuscule, mere milliseconds over a lifetime. Even the GPS satellites orbiting our planet, crucial for navigation, must constantly account for these relativistic effects. Without these tiny adjustments, their timing errors would quickly render them useless. The faster you move through space, the slower you move through time. It's like having a fixed speed limit through space-time. If you dedicate more of your speed allowance to moving through space, you have less left for moving through time. This profound realization shattered the notion of a universal now, suggesting that what is now for you might be the past or future for someone else in a different frame of reference. This brings us to another perplexing aspect: the arrow of time. Why does time seem to flow in only one direction, from the past, through the present, and into the future? We remember yesterday, but we have no memory of tomorrow. A dropped glass shatters, but never spontaneously reassembles. A cup of hot tea cools, but never spontaneously heats itself up. This irreversible nature of events is intimately linked to the second law of thermodynamics, which states that the universe as a whole tends towards increasing disorder, or entropy. Imagine a perfectly organized room. Over time, left to its own devices, it naturally becomes messy. You never see a messy room spontaneously tidy itself. The universe operates on a similar principle. Order gives way to disorder. This increasing entropy provides a direction for time, a cosmic signpost pointing towards the future. It's why processes like aging, decay, and the expansion of the universe seem to only move forward. The universe is, in a sense, constantly forgetting its past, moving towards a state of maximum disorder. But while entropy explains the direction of time, it doesn't fully explain its fundamental existence or why it has a direction in the first place. As we delve deeper into the realm of the incredibly small, the quantum world, time becomes even more enigmatic. Here, at the subatomic level, the smooth, continuous flow of time we perceive seems to fray at the edges. Some physicists, exploring theories that attempt to unify general relativity with quantum mechanics, a theory of everything, encounter equations where time seems to vanish entirely. The famous Wheeler-DeWitt equation, for instance, describes the universe's wave function without any explicit reference to time. This leads some to suggest that time might not be a fundamental property of reality at its deepest level, but rather an emergent phenomenon. Something that arises from more fundamental, timeless interactions, much like temperature emerges from the average motion of countless individual particles. If time is emergent, what then is it emerging from? Perhaps from entanglement, the mysterious quantum connection between particles, or from the way we collect and process information. This perspective challenges our intuition. If time isn't fundamental, then perhaps the past and future aren't truly distinct in the way we perceive them. This ties into the concept of the block universe, a four-dimensional block of space-time where all moments, past, present, and future, exist simultaneously. In this view, our experience of time flowing is merely our consciousness moving through this pre-existing block, much like a spotlight scanning across a fixed landscape, illuminating different parts sequentially. Every moment from the Big Bang to the furthest reaches of the future is already there, laid out like frames in a cosmic film reel. We just experience them one by one. But if time is an illusion, an emergent property, or just a path through a static block, what does this mean for our sense of free will, for cause and effect, for the very fabric of our lived experience? These are profound questions that touch not just upon physics, but upon philosophy and our deepest sense of self. And then there is the question of time's beginning and end. If time began with the Big Bang, the universe's fiery birth, what was before the Big Bang? Scientists often suggest that asking what happened before the Big Bang is like asking what is north of the North Pole. The concept simply loses its meaning. Time itself, along with space, is thought to have come into existence at that singular point. But will time end? If the universe expands forever into an infinite cold void, then time would seem to stretch on eternally, yet perhaps effectively cease to mean anything when all activity and change have faded into a final, frozen stillness. If, conversely, the universe eventually contracts in a big crunch, would time reverse? The answers to these monumental questions remain hidden in the cosmos's deepest layers. Perhaps the greatest mystery of time isn't its speed or its direction, but its very nature, its existence, its purpose, its role in the grand cosmic dance. Time flows through three dimensions of space: length, width, and height. Or does it? What if the stage upon which time plays out is far grander than we've ever imagined? What if space itself harbors secret chambers, hidden folds that exist beyond our perception? Our world, the one you know so well, has length, width, and height. You can walk forwards and backwards, left and right, up and down, three grand directions that define everything you experience, from the vastness of the starry night sky to the intricate patterns on a snowflake. This is our universe, or at least the part of it we can readily perceive. It feels complete, doesn't it? A magnificent three-dimensional stage upon which the cosmic drama of galaxies and planets, of life and laughter, unfolds. But what if, just what if, there's more? What if our universe, immense and awe-inspiring as it is only a small part of a much grander, more intricate reality? What if there are hidden dimensions, silent and unseen, curled up so tightly or stretching out in ways we can't yet comprehend, woven into the very fabric of existence? This isn't science fiction, my dear listener. This is one of the most profound and tantalizing mysteries that physicists ponder as they gaze into the cosmic unknown. Imagine, for a moment, a tiny ant walking along a taut, slender wire or a garden hose. From the ant's perspective, its world is primarily one-dimensional. It can only move forwards or backwards along the length of the wire. If it wants to go left or right, it just turns around. It doesn't perceive a sideways dimension as a significant direction. But we, looking down upon the ant from our three-dimensional vantage point, know there's another dimension available to it, around the wire. The ant could crawl around the circumference of the hose, but this dimension is so small, so tightly curled up compared to the vast length it can traverse, that it's effectively invisible to its one-dimensional understanding of its path. This simple image offers us a beautiful way to think about our own universe. What if there are dimensions in our reality that are just like the around for the ant? Dimensions that are so incredibly tiny, so extraordinarily compact, that we simply cannot perceive them with our current senses or even our most powerful instruments. They might be curled up into loops smaller than atoms, smaller even than the most fundamental particles we know. Imagine our familiar three dimensions as the long path on the hose, and these hidden dimensions as the minuscule, curled-up circle around its surface. They are there, but too minuscule to register in our grand, macroscopic world. Let's explore this idea a little further with another gentle tale. Imagine a world called Flatland, inhabited by intelligent beings who live entirely on a two-dimensional surface. They are geometric shapes, squares, triangles, circles, that can move forwards, backwards, left, and right. They have no concept of up or down. If a sphere from our three-dimensional world were to pass through Flatland, the Flatlanders would only perceive a series of changing two-dimensional slices. First a tiny dot, then a growing circle, then a shrinking circle, and finally another dot, before it vanishes. They would be utterly bewildered, perhaps thinking it was magic, or a shape-shifting entity appearing and disappearing from their flat reality. They would struggle to grasp that the sphere truly exists in a direction they cannot perceive. Now let's turn the looking glass back on ourselves. What if we, in our three-dimensional universe, are like those flatlanders? What if there are higher spatial dimensions, an up or down that exists beyond our current understanding of up or down? Imagine a fourth spatial dimension, or a fifth, or even more. We wouldn't see them as additional directions in the way we see length, width, and height. Our minds, our very physical existence, might be confined to perceiving only three of them, much like the flatlanders are confined to two. These hidden dimensions wouldn't be out there in space, but rather curled into the very fabric of our reality, woven subtly into every point of existence, much like an extra fold in an already intricate piece of origami. The idea of these extra hidden dimensions isn't just a whimsical thought experiment, though it certainly inspires wonder. It arises from some profound puzzles in physics, particularly when we look at the fundamental forces that govern our universe. You see, there are four known fundamental forces: the strong nuclear force, which holds atomic nuclei together; the weak nuclear force, involved in radioactive decay; electromagnetism, which governs light, electricity, and magnetism; and finally, gravity. Now, if you compare these forces, you'll notice something extraordinary about gravity. It is astronomically weaker than all the others. Hold a tiny magnet to a paperclip, and that tiny magnet can defy the entire gravitational pull of the Earth. Think about that for a moment. One small, everyday object overcoming the force of an entire planet. Why is gravity so incredibly feeble compared to its energetic siblings? This hierarchy problem is a deep mystery. One elegant solution proposed by physicists is that gravity isn't actually weak at all. Instead, it might be the only force that is truly able to leak or escape into these extra hidden dimensions. Imagine our familiar three-dimensional universe as a kind of vast cosmic membrane, often called a brain, floating within a larger, higher dimensional bulk. The particles and forces that make up everything we see, light, matter, the strong and weak forces, are largely trapped on our brain. They can only move within our three familiar spatial directions. But gravity, represented by hypothetical particles called gravitons, might be different. Perhaps gravitons are not confined to our brain. Perhaps they can freely propagate like silent whispers into these unseen, curled-up dimensions, or even into larger, unseen dimensions that make up the bulk itself. If gravity is constantly dissipating its strength into these extra dimensions, then from our perspective on the brain, it would appear vastly weaker than the other forces that are firmly tethered to our universe. It's like a grand cosmic faucet that's always dripping, losing some of its flow to hidden channels, making the stream we see appear less powerful. This concept isn't just an explanation for gravity's weakness. It's also a cornerstone of some of our most ambitious and beautiful theories about the fundamental nature of reality, such as string theory and its overarching framework, M-theory. These theories suggest that the fundamental building blocks of the universe aren't point-like particles, but rather tiny vibrating strings or membranes, brains, existing in a space with many more dimensions than we usually perceive, perhaps 10 or even 11 in total. For these mathematical models to work, the extra dimensions must exist, but they must also be hidden from our everyday experience. The brain world hypothesis which suggests our universe is a three-dimensional brain embedded in a higher dimensional space, takes this idea further. It paints a picture of our entire cosmos, with all its galaxies and stars, as just one possible bubble or film among many, floating within a vast, multidimensional ocean. This ocean, the bulk, would be teeming with other brains, other universes, perhaps with their own unique physics and life. It's a truly mind-bending thought, one that expands our sense of cosmic scale beyond anything we've ever imagined. So how do scientists search for these elusive dimensions? It's a monumental challenge, but they're trying. Experiments at particle accelerators like the Large Hadron Collider, for instance, are designed to look for subtle signs. They search for energy that seems to disappear, which could be evidence of gravitons escaping into extra dimensions. They look for new exotic particles that might only exist in higher dimensions, or even for tiny, short-lived black holes that could form if space suddenly curls up in an extra dimension at extremely high energies. The journey to uncover these hidden dimensions is a quest into the very architecture of reality. It's a profound thought that our familiar universe might be just one layer, one tiny facet of a much grander, multi-dimensional existence. It reminds us that the universe is far more mysterious and imaginative than we often give it credit for. It whispers of secrets waiting to be unveiled, of realities beyond our current grasp, inviting us to dream of what lies just beyond the veil of our perception. As you drift deeper into slumber, let this thought gently settle. Perhaps the universe holds secrets not just in its vastness, but in its very fabric, in dimensions we cannot yet see. And with that final mystery softly fading into the cosmic night, our journey through the unknown draws to a close. My dear friend, we gently drift now to the close of our quiet exploration. We've journeyed through some of the most profound and mysterious landscapes of our universe, not with hurried steps or clamorous declarations, but with a soft gaze, a wondering heart, and a peaceful mind. We've peered into the cosmic darkness, not to be frightened by what we couldn't see, but to be enchanted by the luminous questions that twinkle there, like distant, beckoning stars. Tonight, we didn't seek to conquer these grand enigmas, nor to force them into neat, understandable boxes. Instead, we simply allowed ourselves to sit with them, to acknowledge their presence, and to appreciate the sheer, breathtaking expanse of what we still have yet to comprehend. We considered the subtle dance of gravity on a cosmic scale, the elusive nature of dark matter and dark energy that sculpts galaxies yet remains invisible to our keenest instruments. We pondered the very fabric of space-time, the quantum realm's peculiar waltz, and the whispered beginnings of our universe itself. Each one, a vast ocean of not yet known, stretching out before us, inviting humility and sparking a most profound sense of wonder. There is a peculiar, comforting beauty in these unsolved mysteries, isn't there? They are not gaps in our knowledge, but rather luminous invitations. They remind us that the story of the universe is still being written, that the greatest adventures lie ahead, and that the human spirit of inquiry, even in its quietest moments, is an integral part of this grand, unfolding narrative. Imagine, for a moment, the vast silence of space, punctuated only by the gentle hum of discovery, a hum that vibrates deep within our own curiosity. These unanswered questions are the very heartbeat of science, the gentle whisper that guides us forward, encouraging us to look a little closer, to think a little deeper, to dream a little bolder. We didn't come to tonight's journey for definitive answers, but for the quiet joy of contemplation. We allowed our minds to stretch, to embrace the paradoxes, to feel the edges of what we understand, and to gaze beyond them with a sense of peace rather than frustration. There's a profound reassurance in knowing that the universe holds its secrets with such grace, revealing them not all at once, but in gentle layers over eons. It's a dance between the known and the unknown, a rhythm as ancient as time itself. And tonight, we've simply chosen to listen to its gentle melody. As the night deepens around you and your breathing softens into a steady, tranquil rhythm, take a moment to carry this feeling of gentle wonder with you. These unsolved mysteries are not burdens to be carried, but rather luminous companions for our dreams. They remind us that there is always more to explore, more to understand, and that the universe, in its boundless complexity, is a place of endless fascination. It's a place where even the quietest question can open doors to unimagined realms of thought and possibility. So, let these grand cosmic questions gently recede now, not into oblivion, but into the tranquil spaces of your subconscious mind. They don't demand immediate solutions. They simply ask for our patient, sustained wonder. Picture them, not as intricate puzzles causing restless thought, but as soft, shimmering lights far off in the cosmic distance, reminding us of the universe's endless generosity in presenting us with its breathtaking secrets. Tonight, we've simply touched upon the edges of these magnificent unknowns, like ripples on a vast, calm ocean. We haven't needed to understand every wave, every current, but merely to feel the expansive, peaceful presence of the water itself. And in that feeling, there is immense comfort, a deep sense of belonging to something far larger and more intricate than we can ever fully grasp. Now, as your eyelids grow heavy and your thoughts begin to unfurl into the soft tapestry of sleep, know that this journey of discovery doesn't truly end. It merely transforms. In the quiet theater of your dreams, these cosmic questions may continue their gentle dance, inspiring new thoughts, sparking new connections, all in the peaceful, unbound realm of your slumbering mind. Perhaps in the morning, or in the mornings yet to come, a tiny spark of an idea, a new way of looking at an old question, might gently surface from these quiet hours of reflection. Rest now, my dear friend. Let the vastness of the cosmos cradle you in its silent embrace. Let the mysteries of physics, not as problems but as beautiful, open-ended poems, lull you into a deep and peaceful sleep. The universe is a wonderful, mysterious place, and you, with your quiet wonder, are a cherished part of it. May your dreams be filled with gentle starlight and the endless, serene possibilities of the unknown. Good night and sweet, peaceful dreams.